Claisen condensation is how one can make what's called beta keto esters. And again, if that carbon represents our ester functionality, that's the alpha carbon, and that's the beta carbon, hence beta keto ester. For a specific example, we'll use the classic ethyl acetate. And the Claisen involves, again, self-condensation. So we're going to take two ethyl acetate molecules, and in the presence of ethoxide, self-condensation occurs, and we will form the beta keto ester. And this one has a particular name, ethyl acetoacetate. So ethyl because it's an ethyl ester, aceto because it's a 2-carbon unit off the alpha carbon, and acetate because the original carboxylic acid was acetic acid. And this particular molecule is going to be very useful in what's called acetoacetic acid or ester synthesis, because during this reaction we've generated a beta keto ester, and within it the alpha carbon is now not just alpha but doubly alpha. And for the Claisen condensation, it's typical to use a slightly stronger base than hydroxide, so ethoxide or methoxide is typical. And the reason is esters are slightly less acidic than ketones, which are slightly less acidic than aldehydes, and that's because the O of the ester and its negativity won't allow the carbonyl to stabilize an enolate as well as if the O weren't there. So mechanistically, we'll begin with ethyl acetate and ethoxide. And again, locating the alpha hydrogen, which is acidic, and using ethoxide, we can form an enolate. And as we've seen before, this enolate has another resonance contributor, which shows that the alpha carbon has a significant negative charge. And to get from this contributor to that, of course, we would regenerate the carbonyl and push the ene electrons to the carbon. And as we've seen before in self-condensation, it's best to draw another molecule in your mechanism, and those two represent the contributing resonating pairs which the overall enolate has a structure of. And drawing another molecule of ethyl acetate, I suggest in your mechanism, whichever version of your enolate you want to use, draw the alpha carbon of your enolate in close proximity to the carbonyl carbon. And again, nucleophile is the enolate, and electrophile is another molecule of ethyl acetate. And mechanistically, as the nucleophile attacks, we're going to reform the carbonyl as the alpha carbon attaches to the carbonyl carbon, providing this intermediate. And highlighting the key new connection between what was the alpha carbon and the carbonyl. Normally, ethoxide's not a good leaving group, but in this case, it does leave. And remember, originally we had ethoxides, so there's lots of ethanol around. And so in actuality, we don't have to make it leave as ethoxide, but we can make it leave as ethanol. The second thing which allows ethoxide or ethanol to leave is this enhanced stability in this beta keto ester.